In this video, I will show you how to do principal component analysis and factor analysis in Stata. Before you watch this video, please make sure that you have watched my other two videos called Principal Component Analysis and Factor Analysis and Principal Component Analysis and Factor Analysis Example. Click on the link below this video to go to the website and find more information, including the program data and everything else related on this topic. I have opened up here the program in Stata to do principal component analysis and factor analysis. Here's the program, and I have already executed the program. And I'm going to go ahead and open the data so that we can look at it. Okay. So here's how the data looks like. We have data from 50 states. As you can see, we have 50 observations, and these are the states. And then this is the gross state product expressed as a share for agriculture, mining, construction, manufacturing, and so on. And we have 13 variables, and this is the data set that you're going to get up to here. So these are the variables that we have, the original variables, and we will try to find components or factors that are expressing maximum information from these 13 original variables. Okay, so the first thing to do is infile the data. This is where I've placed it. The file is called PCA_GSP. And I will create a global X list for the 13 variables that we have in this analysis. For me, it's agriculture, mining, construction, manufacturing, and so on. So these are the 13 variables. And I will also define a global ID variable. And for me, that variable name is called state. And you may or may not have it. If you don't have it, there's only one command that's not going to work for you, and this is right here. So it's not a big deal if you don't have your observation ID here. And I will use another global variable, number of components, and for me that will be 3, and you will see later on why. So you would need to play with this number yourself, and after you decide how many components or factors you want to retain, just change that number to whatever is the case for your program. So after you change for your data which file to read here, what are your variables from here on, and what's the ID variable, don't worry if you don't have it, and how many components you're going to use, the rest of the program should work for you. You don't have to change a thing. So the first thing to do always is describe the data, and you can see here different variables, 13 of them, and then you can summarize the data, summarize X list, all the 13 variables, and these are the results. As I said, these are shares, and so you see like how these are the means. So there's a considerable variation in the mean, but also from the min and max you can see like how they vary a lot across states, across our observations. So this is why we use correlation for our PCA and the factor analysis rather than covariance, because these categories have different scale for the variables. Next thing you can do is calculate a simple correlation, and you do the correlation of X list, and here the correlation across the diagonal of course are 1. But another thing you see from this correlation matrix is that most of the correlations actually are not very high. I mean, we have minus 0.5 here and so on, but many of them are like, this is really not significant, it's just so small. Many of the magnitude. So we're here on the borderline of whether or not to be applying PCA and trying to get, as you know, the more correlated your data is, the better, because then it means you can extract those components and factors. And the more uncorrelated it is, the harder it is to apply these methods. Okay, so the next thing to do is come up and estimate a principal component analysis. And the way to do that is the command is PCA of XList. You put here all the variables you want a principal component analysis of. So again, we have 50 observations, number of components, and the original variables are 13. Okay, so these are the components from 1 to 13, and these are the eigenvalues associated with each component. Okay, and so here are the first eigenvalues, 3.23, a very high one, then 2.23, and so on. So we can see that the first 5 components are above 1. And this difference is, again, this value minus that value is the difference here. So you can see how much each additional component, the difference in the eigenvalues is. And here, this proportion and cumulative, this is the proportion of variation explained by each of the components. So here, the first component, actually, the first component explains 24% of the or 25% of the variation in the data. The second one explains 17%. So cumulatively, they explain 42%. Next one is 15%, so 57%, and so on. So see, if we're using 3 components, we're explaining up to 57% of the variation. And with 5 components, this line here, we're explaining 76% of the variation. So this is pretty good. So again, the Kaiser rule says that if we have components with eigenvalues above 1, we should retain them. So according to this, we should retain 5 components. Or if we see that these are not contributing as much, in terms of variation that they explain, or there's a significant break between them, then you could go with 3 components. And I will talk about this a little bit later on again. So here are the different eigenvectors, and they're calculated here, and I will explain them later on. So notice that now we have all the eigenvectors here for all 13 components, and then we're going to limit them just to the first 3 or first 5. So the next thing to look at is what we call the Scree plot of the eigenvalues, and you could do that as a Scree plot, just that, or you could put comma and y line equals 1, and that will just put you put a line at the value of 1. Okay, so here is the graph. After you execute this line, this is what you're going to get. And these are exactly the same eigenvalues. So you see the first component has this eigenvalue of 3.24. Second one has 2.23, and so on. So these are all the 13 components, and we see that the first 5, 1, 2, 3, 4, 5, have eigenvalues above 1. But you see how, like here, there's just a slightly bit higher break, not very much. But because of this break here, I'm going to go ahead with 3 components for the rest of the analysis. It's perfectly fine to go with 5, and that's the best rule, is if it's above 1, if a component has an eigenvalue above 1, just go with that, with all of these components. So, okay. So the next thing to do is now you could do a principal component analysis with the correct number of components. So one thing to do is PCA of XList, and you could put comma minimum eigenvalue 1. So here Stata knows exactly how many to retain in your program. So for me, it happens that 5 components have that eigenvalue above 1. For you, maybe 2 or 1 or 7, whatever the case is. So the next command, this one, will estimate exactly 5 components, because the first 5 have these eigenvalues above 1. So that would automatically be decided for your problem. Okay, so we can see that these are the what we call the loadings on these principal components, and these are the original variables that we have. And here we can see the percent of variation that is still unexplained. So with 5 components, we're doing pretty good. 27% is unexplained, so the rest is explained. That's pretty good. And you see these numbers are fairly low, and this is what we want to have. But as I said, let's try to go ahead and estimate a principal component analysis with only 3 components. And here that number of components, I'm reading just the number 3 from up above here. So you can put here as many as you decide, regardless of what the minimum eigenvalue of 1 is, how many the program decides for you. So this is the PCA with now 3 components. You can see the top of the chart is the same. The bottom now only has 3 components, which are identical to the 5 above. I mean, the first 3 are the same. The 3 here are the same as the first 3 from the 5 above. But the unexplained variation is a little bit higher. Now it's 27% or something up in the previous case. Now it's 65. So if we only use 3 components, we have actually a lot of variation left unexplained here. And this one is also not explained very well. And this one, you see like how they're kind of high numbers. So maybe you should go with 5, for your analysis. Okay. So just to make things a little bit more readable, one thing that you can do is put blanks. And this statement right here, blanks of 0.3, means that if the absolute value is above 0.3, they're going to just, if the absolute value is below 0.3, it's actually going to put a blank. And so it's easier to see. So this table now, it will have blanks on this number right here, this number, and so this one is above 0.3, so it's going to keep it. So this is what this next result is. You see like how now the blanks are there. So these are the loadings, the principal component loadings on the different original variables. And so they actually represent the correlation between the component and the original variable. And so here are very high correlations with the original variable. So you see the first component loads very highly on mining, transportation, trade W, real estate, and services. This is the second component, what it loads on, and the third one, and so on. So another thing that you can do here is try to name the components based on what it loads on. So in this case, it's not very easy since it's not like a nice survey or something, and see how these group. But you could say like for this component, it loads high on agriculture, manufacturing, trade, and real estate. So you can try to name it something based on those variables that you have in the data set. So next thing that we talked about in the previous videos are how to do component rotations, and you could do several different ones, and I've just tried here a couple of them. And you could do rotate, vary max, and here you could put the blanks again, and then you could clear this rotation. So now these component loadings that we have here, we're going to rotate them a little bit. And these are the results that we have here. So these are the vary max rotation, and these are the ones with the blanks. So, okay. So if you look at these, technically they should have fewer of these factor loadings, and they should be more distinct among components to kind of ease interpretation. And they should be uncorrelated in the case of vary max rotation because it's an orthogonal rotation. And so now again, you could try to explain here, which ones of the original variables load on component 1, component 2, and component 3. And like, for example, see this component 2 here, you have communication and real estate and services loading very high on this. So you could say that this is the more communication and services kind of thing, as opposed to the agriculture and the manufacturing and the construction and so on for the other components. So you could possibly name them something. Okay, so now that you can estimate another one called Promax, and here a little bit different rotation, which actually in reality, if you look at the other video, these are the same magnitudes to the previous one, so it's not, the rotation hasn't produced much different results. Okay, so after you do rotation, you can clear these rotations by using rotate comma clear. Okay, so we're done with rotations, so now we can do is scatter plots of the loadings and the score variables. So if we do a loading plot, this is the graph that you will get. Okay, so these are the loadings of the components, and these are the 13 original variables that we have here. You have services, communication, trade, and so on, and this is how they load in the component space. So if I just put this next to each other, you can see how, like, let's pick mining. Mining, oh wait, well, these ones have rotations in them and these ones don't. But if you scroll back up in this file, you can see that mining, let me go ahead and scroll back up. Okay, so these are actually the unrotated ones. So let's try that again. So if you look at mining actually loads very high on component 1 with 0.46 and almost nothing on component 2. So you see on component 1 we are at 0.46 right here, and we are at, you know, a very low number for component 2, and so on. So these correlations right here of the original variables with the two components are represented right here, and you could see them. Transportation right here has very high loading on factor 1. Trade W has a negative loading, and so on. So these are the, again, this is the loadings plot that we can interpret. Now another thing that we can interpret is the score plot. And so the score plot would be this graph right here. Okay, so this is this, after we execute score plot or score plot, and here comma label, and you can label the IDs, which for me are state right here. This is what you will get. And these are now not these are not like the original variables like we had in the loadings plot. These are the observations. These are the rows in the data. And the other ones, the variables, are the columns in the data. So now we're plotting the observations or the rows in the data. And you can see how the observations load on these now two different components that we have. And you can see like Alaska here is a big outlier, and Wyoming are big outliers. And I will show you when we actually look at, when we're predicting the scores in the next step of the program, I will show you why these are now outliers. But that's how the data looks like. It's helpful to see your data. Okay, so the next thing to do here is you can actually estimate the loading and the scores of the components. And if you execute that line, these are the results. Okay. So we have here again the loadings of the different components, and here we can actually be predicting the scores, or the principal component 1, 2, and 3 that go in the data. So these are the scoring coefficients that you have, and those you can see are the same as above here, as the loadings. And so if you actually predict, then you have to put as many components as you've estimated in the data set, and you put comma score. And if you actually look in the data, you could actually see them here because we now appended them to the rest of the data. And so here are the components that we have here. And notice that now the 13 variables that we have before, these are the variables, the original variables in the data, are now summarized by these three components that we have here. So again, these three components capture considerable variation in the data, and we could just go with 3 components rather than 13 variables. But you see they have like different values. And now what we plotted on the score plot, this one, was the PC1 versus PC2. And you see like how this one is a big outlier here, and if you scroll down, this 2 would be exactly Alaska. You know, so that was the outliers that we plotted on the score plot. Okay, so the next thing to do is you can estimate the KMO measure of sampling adequacy. So if you go ahead and run that command, this is what you're going to have here. And again, a number above 0.5 is good. It means that we're justified in using principal component analysis. And unfortunately, in the example that I have here, they're not above 0.5. So we're not really justified in using principal component analysis. The correlation isn't too high among variables, but I can show you here that, you know, what I've shown you is that even when we have a case like that, you know, we still have very high, I mean, we can still apply principal component analysis and get some decent results. Okay, so that was the principal component analysis. And factor analysis, I actually put it here because it's just so related. It's very much the same. So I'm just going to concentrate on the differences here. So the way to estimate factor analysis is you put factor and then you put all your x variables in a long line. For me, that's x list. You see here you use the same thing to decide how many factors to use, and here are the different factor loadings matrix. Now, while this table above here is the same as the principal component analysis, it's identical, this one isn't. The factors are actually different than the components if you scroll back up. So the next thing to do is how many factors or to use. You use the Scree plot, and because the eigenvalues are the same, you make the same conclusion. So again, you can let the program automatically decide how many with minimum eigenvalue equals 1. So it's going to use 5 components, and these are now the factor loadings on those 5 factors. And this is the uniqueness of this factor. So here we have uniqueness versus commonality instead of unexplained variation. So this is how the common factor model works. And again, the uniqueness is reversely related to commonality, which is 1 minus this value. So uniqueness is basically, you can think about the error term of this variable that's not explained by the common factors, and the commonality is what is explained by the common factors. Okay, so here you can estimate factor analysis with as many factors that you want to, and I've specified this above in the program as 3. So these are just keeping just 3 of the 5 factors, and here you can again put a blank of 0.3 so that you have some of the, if the loadings are less than 0.3, then they're blanked out. Okay, so again, it's a bit difficult to interpret these results just because we have so many of the original variables load on so many of the factors, so it's kind of hard to see how they group and cluster together. So what we may want to do is different rotations, and again, I'm going to try 2 rotations, Varimax and Promax, and these are the results here. and these are the results with the blank. So again, we can see, again, too many of the variables load on your factor. So hopefully in your data, you're going to have the first few variables load on the first factor, the next variables load on the second factor, and so on. It will be a better story. But you can look at these and try to name a factor based on what it loads on. Okay, you can do exactly the same thing with the loadings plot and score plot, and I can show you these. So these are the factor loadings, and you can see now they are structured a little bit differently between factor 1 and factor 2. These are the original variables from the data and how they are loading in the factor space. Okay, and then the last thing is we can see again the scores of the variable, and again this is factor 1 and factor 2, and again we have these outliers here that have very high values of the factor 1 in the data. Okay, so we did that. We can predict the scores of the factors here, and you do that by saying predict F1, F2, and F3. And if you look at the data, here, these are the factors that we now put in the data. You see factor 1, 2, and 3, and you see they're actually different than the components that we estimated before, but this Alaska still has a high value of on factor 1, a high factor score for factor 1, and that's the outlier. Okay. So again, instead of using the original variables, we can use these factors. And as you can see here from what we've done on the factor analysis is very similar to what we've done for the principal component analysis. So again, the reason of using one versus the other is more theoretical, and do you have a reason to believe that factors are driving your data or not? Okay, so the last thing is to show you the KMO, again, measure of sampling adequacy that we discussed above. And again, we don't have values that are above 0.5, so we're not very much justified in using factor analysis. Okay, so I think that's what I had about principal component analysis and factor analysis in Stata. Thank you for watching.